Alright, so this video is meant to really consolidate a lot of the principles and laws that kind of govern our arithmetic with vectors. So last lesson we talked about vector addition and subtraction, and with this lesson we're just going to sort of learn some of the do's and don'ts of vector addition and therefore subtraction as well. So almost all of these are pretty intuitive and kind of go without saying, but for the sake of, formalizing a lot of these laws, let's cover a couple of these. So the first one is the vector addition law of closure. That basically means that if you were going to take two vectors and add them together, the result would be a vector. So the sum of two vectors is an element of all vectors. So basically it will yield us a vector. Commutative property, actually I believe we touched on in the last video, was that the order in which you add vectors has no significance, which is basically the same principle as it is with numbers. 3 plus 5 is 8, and 5 plus 3 is also 8. Vector A plus vector B is the same thing as vector B plus vector A, because the resultant vector would be the diagonal of a parallelogram. We also talked about inverse or opposite vectors last time. If we were to take a vector and add its opposite, they would cancel each other out. So essentially, going one way, one direction with a certain magnitude, going in the opposite direction with the same magnitude would basically bring it back to square one. So they would add up to the zero vector. Taking a vector and adding the zero vector to it makes it remain unchanged, and that should also kind of go without saying. Adding nothing to something doesn't change it. Finally, the associative property, which is kind of related to the commutative property there, big picture here, the order in which you add vectors does not matter. I could draw a big diagram and prove that case, but we're not going to get into that for the sake of the argument here. If you added vectors A and B and then added C, that would be the same thing as adding vectors B and C and then adding A to them. Okay, so very closely related to that commutative property. We also touched on scalar multiplication with the last lesson. So this first principle of scalar multiplication should be pretty simple or pretty straightforward. If you were to take a vector and multiply it by some value k, the result would be a vector again, but it would be a vector that had been stretched. So we talked about that being a stretch factor of 3, for example, so stretching vector A by a factor of 3. However, of course, if that stretch factor were negative, we would be taking the vector and turning it in the opposite direction. So that's what that negative does. And multiplication by a fraction would compress the magnitude of that vector. So you can see by these three diagrams, if we started off with this vector A multiplied by 3, it's 3 times longer, same direction because 3 was positive. And if we took the vector A and we multiplied it by negative 1/2, it would turn in the other direction because of the negative, and it would be half as long in magnitude because it is 1/2 vector A. Along with both of those come some other laws that also kind of go without saying. Multiplying any vector by 1 is going to leave it unchanged. We know that about multiplication by 1. And also multiplication rules all apply. Distributive property applies. So if I was going to take the sum of two vectors and multiply them by a scalar, that is the same thing as each individual vector multiplied by that same scalar separately. Okay, so, and that also works in reverse, right? So again, we can do distributive property in reverse, and we can do it forwards. Order doesn't matter when we're multiplying a scalar by a vector, and that's also kind of important to touch on a little bit later on when we talk about cross product and dot product. Okay, so go ahead and give this a try, because basically, if you know how to do basic algebra, you know how to do algebra with vectors too, right? So you have here an expression where we're basically taking a couple of scalars, so, the number 5, for example, and we're multiplying it by the sum of a couple of vectors, then we're subtracting that vector there too, and we're subtracting all of those vectors. So go ahead and do what you would think you would need to do, and you'll probably be right. So go ahead, pause the video and try that algebra. Okay, so hopefully you got the same answer as I did. If you did, go ahead, fast forward a little bit, jump ahead in the lesson. If you didn't, maybe have a look at my solution here. So just as we mentioned on the previous slide, I'm going to do distributive property with that 5. 5 times A, 5A, but A is now a vector and not a variable, right? So 5 multiplied by 3 vector B would give us 15 vector B, and 5 multiplied by negative 2C, or vector C, gets us negative 10 vector C. We also distribute that negative or minus sign. Subtracting a positive 4 vector A would give us a minus 4 vector A. Negative, negative gets us a positive. Subtracting a positive gets us a minus. We also distribute this 2 into that set of brackets. So 2 multiplied by 2A gets us 4A. 2 multiplied by negative 4B gets us negative 8B. And 2 multiplied by positive 6C gets us positive 12C. Okay, but we're not done there. These are basically, again, there are a couple of like terms in here, right? So 5A minus 4A plus 4A winds up getting us 5A. Because if you want to think about it this way too, this negative 4 vector A and this positive 4 vector A cancel each other out, essentially. They're the 0 vector. Positive 15B plus 7B minus 8B gets us 14B. And negative 10C minus 9C plus 12C gets us negative C. So that's essentially how that one shakes down. So I have a question for you here, and basically I'll rephrase the question a little bit for your purposes. What can we say about 3 vectors whose sum is 0, or whose sum is the 0 vector? What I want you to do is try and draw a diagram. Try and draw me a diagram of 3 vectors, and that when they're added up, give us a 0 vector, and try and contemplate what that gets you. Just pause the video and think about that for a sec. So essentially, here's the answer. Hopefully you drew a triangle. Because if you think about it, if you took 3 vectors and you added them together and you wound up with the 0 vector, you wound up back at your beginning or back at your starting point. So if you think about it, 3 vectors that add up to the 0 vector create a triangle. And so a group of vectors, whether there's 3 of them or more, will, when added together, create the 0 vector, are called an so a group of vectors, whether there's 3 of them or more, when they add up to the 0 vector, that would be an example of what we call an equilibriant, basically, that all 3 of those vectors are kind of canceling each other out and neutralizing each other. So a triangle in this case, any closed polygon would basically do that for multiple sides. All right, so here, give this one a try or a think. We've got vectors u and v are unit vectors, and the angle between them is 30 degrees. We saw a very similar question to this with the previous lesson. So what I'm asking you to do is draw vector 3u minus 2v, and then I want you to calculate the magnitude of that resulting vector. So go ahead and draw a diagram. You know, question A, I probably actually wouldn't even ask that on a test, right? I'd just say, calculate the magnitude of those two. You'd have to draw that diagram, right? So no matter what, draw a diagram whenever we're dealing with a vector problem. Okay, so go ahead, draw that diagram and calculate that magnitude for me. Okay, so here's the full solution to this example. Really similar to something we did on the previous lesson, so I'm not really expecting too much difficulty with this one. I started over here with a quick diagram to just sort of suss out what angle we're working with. I didn't put it in there, but maybe it might be useful if I put the number 1 there and the number 1 there, because we were told they were unit vectors to start off with, right? Maybe if I had given magnitudes for them, this question might be a little bit more difficult, but because we said they were unit vectors, they're judged as a magnitude of 1. So if I was to take the vector 3u, that basically means I'm going to take the vector u and I'm going to extend it for 3 units. So basically it has a magnitude of 3. The catch here that's maybe a little bit different from previous lessons is that we're actually subtracting 2v. If we're subtracting 2v, we're going to go in the opposite direction. So you can see that this green vector is going from the left to the right. If we're going to subtract 2 of it, we're going to go from the right to the left 2 units as opposed to 1. Right? So again, this diagram here to the right is not to scale at all, right? But it's a pretty good rough diagram. Recognizing that once we do that, once we double back like this angle on the inside of the triangle is also still 30 degrees for a myriad of reasons. I think the easiest way to demonstrate that is to think about this, is if I was to extend this green line and extend this blue line, I've created a mini version of the diagram that I originally had, which means that this angle right in here has to be 30 degrees. And if that angle right there is 30 degrees, that angle right there is also 30 degrees according to opposite angle theorem. Okay, so not only does it look like it's 30 degrees, but it is indeed 30 degrees. From there, if we needed to find our magnitude of that we are going to use Coase law again. We're solving for this side. I labeled it A. A squared is going to equal 2 squared plus 3 squared minus 2 times 2 times 3 times cos 30. So if you pump that into a calculator, you make the calculator work for you, you'll get an answer that's approximately 1.6. I mean, again, that's a rounded value. If you wanted an exact value, you'd use the exact value of cos 30, and you'd also have a square root sign on top of a square root sign, so that'd be a bit of a pain. So I'll just round that answer there because the question didn't specify. So here's a third example. Given the vector diagram below, I'm asking you to draw vector A minus 2b plus 3c, and then calculate the magnitude of that. So again, this is kind of a little bit more of an extension of what we just did and what we did yesterday. So try this one. Try to draw that diagram first, and then of course, once you've got that diagram, try to grapple with what the magnitude of the resulting vector would be. And obviously, you're going to have to use some trigonometry. So you might be wondering why I said use trigonometry when the diagram that you have before you is not exactly a triangle. Hopefully you kind of know enough about trigonometry to know that if you break that shape into two pieces, you're going to wind up with two triangles, right? So this is a bit of extra trigonometry for you. Okay, so step one is basically us discovering what the magnitude of a minus 2b is. Okay, so I'll call that x. I guess we'll start off with x's and y's. Again, we don't want to use a and b because a and b were vector names as well. Hopefully I didn't lose anybody here with the 45 degrees. We know that that's 45 degrees, similar to what we had with the last question. And hopefully I didn't lose anybody here. I went to the left 2 units because we're subtracting 2b. See how vector b is going from left to right in the original diagram? If we're subtracting 2b, we should be going from left or from right to left. Okay, so a good place to start would be to solve for this green x. So again, Coase law is pretty much what you're going to use, so that x squared would be equal to 2 squared plus 1 squared minus 2 times 1 times cos 45. And that would mean that x equals roughly 1.47. Just a bit of quick calculator work and rounding. So now that we know the value of x equals 1.47, we can use that green information to solve for this purple value if we know some angles. So we again have to flip back to a little bit of thinking here. We know that this angle right here is 45 degrees. And now what we're going to do is basically take that 45 degrees and subtract from it the value of this green theta that's inside here. Okay, that's that angle right there that I'm kind of highlighting in green. If we subtract that, that'll give us the other piece of the pie. Okay, so those two angles do add up to 45 degrees, and we can determine the value of this green angle by using sine law. Right? So if I set that up, I labeled it theta, so I'll call it sine theta. Its corresponding side is a value of 1, right? Opposite to that is 1. That should equal the sine of 45 over 1.47, because this 45 degree and that 1.47 that we calculated are opposite to each other. There's no real solving that needs to get done there other than a second function sine on a calculator. Theta equals 28.8 degrees. And so then to determine the value of the angle inside, this guy down here, I'll label it in blue, we basically just do 45 minus 28.8 degrees. And that gets us 16.2 degrees. So now that we know this blue angle in here is 16.2 degrees, that's this guy right here, we can use the information that we have now to solve, right? We have x, which is 1.47, we have 3, and we have the 16.2. So we're going to use Coase law again. I'll label this y, or vector y, I should say, and probably label that as vector x. And we can use Coase law to solve for vector y. Vector y squared, or magnitude of vector y squared, I should say, is equal to 1.47 squared plus 3 squared minus 2 times 1.47 times 3 times cos of 16.2. Sorry, that looks like a 7. 16.2. This should all work out to 1.6. Okay, if you pump that into a calculator correctly. So that's pretty much it. Just a couple of more in-depth examples, getting you to think a little bit more about vector diagrams. Again, I can't emphasize it enough. Draw a good, accurate diagram, and solve from there. It all stems from a well-drawn diagram. Take the time, take out a ruler if you really need to, if you want a good scale diagram. Get kind of comfortable with that. Make sure that your trig is up to par. If you're making little mistakes in terms of solving for coast law or setting up coast law, it is really going to wind up costing you here, okay? But pretty much nothing new, hopefully, out of this. So just go back, do a bit more practice, and continue to improve. Thanks for watching.